Hi, everyone. So welcome back. We are looking at section 4.8 today. And you may be looking at the title and thinking, what the heck is that? So that is pronounced L'Hopital's rule, L apostrophe Hopital, L'Hopital's rule. Now, there's actually two ways to spell this. So you could also see it spelled L apostrophe Hospital. So it's like La Hospital, but don't pronounce it La Hopital or La Hospital. It's L'Hopital. Um, so this is called L'Hopital's rule. So this fun story is named after a guy who did not actually do the math for this rule. So this is a rule that will actually make our lives a lot easier. So a little bit of math history for you real quick. Um, L'Hopital was not a mathematician. So L'Hopital was just a guy. I think he was like a businessman. And he bought math from someone else. So back in the day, it was a very common practice for people that did math to sell their math because maybe they needed money and maybe they had math that was really, really big, really important that could make a name for someone. So they would sell their math. And so this guy, L'Hopital, said, hey, I really like this idea. Can I buy it from whoever it was that he bought it from? And he bought it. So this is now known as L'Hopital's rule, but as with most things in math, L'Hopital did not have anything to do with it. There's so many instances, like Pythagorean's theorem. He was not the first one to come up with this idea. So anyway, fun little math lesson for the day, math history lesson. All right, so first let's start with like a little reminder of what it means to be an indeterminate form. So what we've maybe seen in the past is an indeterminate form would be 0 over 0 or infinity over infinity or like 0 over infinity or like infinity over 0 or just some number over 0. So anything that you can't directly compute is going to be an indeterminate form. Well, now we're also going to consider a few other situations that would be an indeterminate form. And the idea is anytime we see an indeterminate form like this, we can use L'Hopital's rule to compute the limit of this function. We'll be looking at limits. So now we can also consider 0 times infinity, which is an indeterminate form. You would think it's 0, but it's not technically 0. Infinity minus infinity, because some infinities are in fact bigger than others. 1 to the infinity, because infinity is not a number. We can't compute that. 0 to the infinity to the 0. Though a number to the 0 is 1, infinity is not a number, so this is indeterminate. And then 0 to the 0 is also indeterminate because though a number to the 0 is 1, 0 to the 0 is not a proper form. All right, so if we see any of these situations, we're going to have to use a rule, and that will probably be L'Hopital's rule to solve this. All right, so first let's actually get down what L'Hopital's rule is, because I keep using the terminology and then not telling you what it is. So let me tell you what it is. So suppose f and g are differentiable, which again, pretty much always suppose things are differentiable. If it's not, then we have no reason to do calculus. Over some open interval. Again, it's probably going to be given that you're in an open interval. I'm not going to trick you with a case that is like not in an interval, except possibly a. So that could be like if you have a absolute value, you're not differentiable at a single point. Okay. If the limit as x approaches a is 0 and the limit as x approaches g is 0, then the limit as x approaches a of f over g is equal to the limit as x approaches a of f prime over g prime. So, first of all, what I want to note is it doesn't have to just be 0 over 0. It can, in fact, be any of these indeterminate forms. Any indeterminate form you see, you will use L'Hopital's rule. So while this is accurate, add all of those to it. Also, this is a very big statement because typically if you saw something over something else, say this was like a rational function and they were both polynomials, the only way that you would think of computing this far is going to be the quotient rule. But L'Hopital's rule is actually a really big rule that like it may take you a second to like grasp the gravity of this rule. It says that you can take the derivatives of these rules of these parts of the function separately. So you can look at just the derivative of the numerator and just the derivative of the denominator and then try to evaluate it again. So this is a really, really important concept that helps us and saves us so much time. And essentially, what we can say is if this doesn't work, say you plug it in, you still get an indeterminate form. Then we also have the limit as x approaches a of f double prime of x over g of x is equal to this, which is equal to the original. And essentially you can take as many derivatives as you need to get you to the answer. So that's the cool thing about L'Hopital's rule. If you have to take 4 or 5 derivatives, it will probably eventually get you to the answer. All right. If you're curious why this works, why we don't have to use the quotient rule, and why L'Hopital's rule just does work, this is the proof of the rule using just a very simple explanation. So I'm not going to go through it. I'm not requiring you to know the proof, but I know there's a lot of people that like to know why things are the way they are. So if you'd like, you can stop this and read through it just to get a little bit more of an understanding. Again, I'm not going to go through it, but I would like to present this to you because I know it's kind of weird when I've told you time and time again, like if you see a fraction, you have to use quotient rule. And now I'm saying, well, never mind. If it actually has these forms, go ahead and use L'Hopital's rule. So this is why. All right. Okay, so let's take a look at some examples. Evaluate each of the following using L'Hopital's rule. So the first step is always going to be trying to plug in. Like I mentioned in the previous video, 99.9% of the time, it's not going to work. You're going to have to use a rule. That's just calculus for you. All right, so if you plug in 0, this is the limit as x approaches 0 for a. The cosine of 0 is 1. 1 minus 1 is 0. This is 0. This is 0 over 0. That's indeterminate form, so we have to do something about that. So what we can do about that is we can use L'Hopital's rule. So here's a. We can now take the derivative. So what this says is that this is equal to the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator. So the derivative of 1 minus the cosine of x is, well, the derivative of 1 is 0, and the derivative of negative cosine of x is positive sine of x, because we remember that the derivative of cosine is negative sine, but negative times negative is positive. Over the derivative of our denominator, which is x, is just 1. Now we can try plugging in again. Well, we just are dividing by 1, so whatever answer we get is a valid answer here. The limit as x approaches 0, well, that's just plugging in 0. The sine of 0 is 0. And this does require you to remember your trig values. All right, and that's just the answer. So now let's look at B. Again, now we're looking at the limit as x approaches 1. So if you plug 1 into the sine of pi x, that's just the sine of pi, but the sine of pi is going to be 0. And the natural log of 1 is 0. So again, we get 0 over 0. That's a problem. Now let's use L'Hopital's rule. So that tells us that we can consider still the limit as x approaches 1, but now take the derivative of the numerator and the denominator separately. So the derivative of sine of pi x, well, the derivative of sine is the cosine of pi x. But since we have something other than just a regular x in our argument, we have to use the chain rule. So now we multiply by the derivative of the argument. The derivative of pi x is just pi, because you can think of pi as a constant, which it is. Pi is 3.1415, and it goes on forever. So if it was like 3x, it would be 3, right? So this is just pi. I'll multiply that up front. So this is the derivative of the numerator over the derivative of the natural log of x is 1 over x. Now we can try to plug back in and see if it works. So plugging in 1, cosine of pi is going to be negative 1. So this is pi times negative 1, which is negative pi, over 1 over 1, which is just negative pi. So we do, in fact, get an answer. So you notice how this gives us so much more freedom when it comes to solving our limits. You'll also remember from section 4.6 that when we were looking at rational functions, we were looking at the highest degree in the denominator and dividing. And while that is entirely a valid way of doing it, and actually the reason why L'Hopital's rule for polynomials will work, we don't have to do that anymore necessarily, unless I specifically say solve this thing without using L'Hopital's rule, like solve it by hand. You can just solve it using L'Hopital's rule now. All right, let's take a look at C. So again, you plug in infinity. This is e to the 1 over infinity. Well, 1 over infinity we know is 0. E to the 0 is 1. 1 minus 1 is 0. Okay, so the numerator is 0. 1 over infinity is 0. So it's 0 over 0. Let's use L'Hopital's rule. So this is the same thing as saying the limit as x approaches infinity of the derivative of the numerator over the derivative of the denominator. The derivative of e to the 1 over x, well, the derivative of an e function is that you keep that e the same, but then you multiply by the derivative of the exponent. Well, I'm going to pull this up here. So 1 over x is the same thing as x to the minus 1 using our exponent rules. And the derivative of x to the minus 1 is just power rule. So that's minus x to the minus 2, which is the same thing as saying negative 1 over x squared. So that's what we're going to write. This is the derivative of 1 over x. So this is times negative, and this is the whole thing times not in the exponent. Negative 1 over x squared. The derivative of minus 1 is 0, so we don't have to write that, over the derivative of 1 over x, which we just did conveniently. We don't even have to do it again. This is negative 1 over x squared. And would you look at that? This cancels out with that. And what we're left with is the limit as x approaches infinity of e to the 1 over x. Well, plug in infinity. This goes to 0. E to the 0 is 1. So we get an answer of 1. Let's take a look at the last one. Here's D. Again, try to plug in 0 here. Sine of 0 is 0, minus 0, that's 0. So on numerator 0, 0 squared is 0. So that's 0 over 0. So that means we have to use L'Hopital's rule. So we have the limit as x approaches 0 of the derivatives. So the derivative of sine of x is cosine of x minus the derivative of x is 1 over derivative of x squared is 2x. All right, now we'll try plugging back in. I'm not even going to plug into the numerator because right away I see there's an issue with our denominator. When I plug 0 into 2x, I get 0, which means we have to do it again. We have to do it until we don't have to anymore, until we don't get a 0 in our denominator or some form of indeterminate form. So we'll take another derivative. The derivative of cosine is negative sine of x. The derivative of minus 1 is just 0 over the derivative of 2x is 2. I got to remember that my limit is still in here as x approaches 0. And now I can try to plug it in again. Plugging 0 into sine, that's minus sine of 0 is 0 over 2. But be very careful to remember you can have 0 in your numerator as long as you have a number in your denominator. So something divided by 0 divided by something is 0. So your answer here is just going to be 0. All right, let's take a look at a few more examples. So if you remember, this was exactly one of the questions that we did using the divide by the highest degree in the denominator method, except it was really long when we did that. So let's do the absolutely shortened version. This is where I do the typical math teacher trope of, well, we had to do it the hard way first because you have to understand where we're coming from before we do it the easy way, right? But that's actually the case here. You have to understand it both ways. So let's go ahead and show you the easy way of doing it. So obviously plug in infinity, we get infinity over infinity. That's indeterminate form. Boo. Let's use L'Hopital's rule. So this is the same thing as the limit as x approaches infinity of the derivatives. Derivative of 3x plus 5 is 3. Derivative of 2x plus 1 is 2. The limit of a constant is a constant. That's 3 over 2. That's a lot less work than what we did. But there will be a chance that you could be asked for the algebraic way of doing it. So it's still very important that you understand both ways of doing that. All right, same situation here. Look at the limit is limity. Wow, I just combined many words. The limit, as you can tell, I've been doing this kind of all day. The limit as x approaches infinity of the natural log of x over 5x. Well, the natural log of infinity is infinity, and 5 times infinity is infinity. So you have infinity over infinity, which is indeterminate form. So we'll use L'Hopital's rule, which tells us that this is equal to the limit as x approaches infinity of the derivative of these two things. The derivative of the natural log of x is 1 over x, over the derivative of 5x is just 5. We can try plugging in now. Well, the 1 over x will go to 0, and 5 just stays the same. And so this whole limit just goes to 0. This was also, I believe, one of the examples that we looked at. And we're once again going to show that it's so much easier if we use L'Hopital's rule. So again, plug in 1. What we'll get is 1 plus 5, that's 6, which is 5. Oh, this is not an example we looked at. Consider this, show that the limit cannot be evaluated using L'Hopital's rule. So as always, what we've been doing is we've been checking to make sure we have indeterminate form. So what we're going to do is we're going to show that if we don't have indeterminate form, it doesn't work. So first, let's do the direct limit computation. So the limit as x approaches 1 of x squared plus 5 over 3x plus 4, we know we can just try plugging in right away. So this is 1 squared plus 5 over 3 times 1 plus 4, which is 1 plus 5 is 6 over 3 plus 4 is 7. Because we were able to directly compute the limit, we know that this is the answer. Period. End of story. This is the answer. Let's show that we can't use L'Hopital's rule. So let's take the derivative of the numerator and denominator separately. So we can maybe, question mark, say that this is equal to the limit as x approaches 1 of, well, let's take the derivative of the numerator. So this could be 2x over the derivative of the denominator, which is just 3. Well, now that we've taken a derivative, we could try to plug in our value, and what we get is 2/3. But 2/3 is not equal to 6/7. So since no indeterminate form, we cannot use L'Hopital's rule. All right, so it's very important that you check to make sure that you do, in fact, have indeterminate form, because otherwise it's not going to work. You'll get an answer and you may feel like it works, but it's going to be the wrong answer, because the correct answer here is just going to be 6/7. All right, we only have 2 more examples. So again, I'm trying to make up for that one day that was an hour-long lecture. So this is going to be a shorter lecture like yesterday's. All right, 2 more examples. So these are going to be kind of funky looking examples though. So this is evaluating the limit as x goes to 0 from the right of x times the ln of x. As we see, if we try to plug in 0, you get, well, since it's from the right, this is why we have to specify, because the natural log of x is not defined coming from the left, because the natural log of x looks like this. And so there is no value at 0. So we only can look at it coming from the right. So coming from the right, we get a value of negative infinity. But then at 0, it's 0. So we have it 0 times infinity form, which is a type of indeterminate form. Because we have indeterminate form, we can use L'Hopital's rule. But L'Hopital's rule says that we can only have the limit as x goes to a of f of x over g of x. And you notice here we have what appears to be a product rule. And L'Hopital's rule says nothing about product rule. You can't use product rule with L'Hopital's rule. So what we have to do is we need to make it into a quotient. We can't do anything with the natural log. Absolutely nothing. Natural log is what natural log is. So the only thing that we can adjust is going to be this x. So what I can do is I can write this x. Well, if this is x to the 1, I can say, well, this is the same thing as x to the negative 1 to the negative 1. Well, x to the negative 1 is the same thing as 1 over x, so this is the same thing as 1 over x to the negative 1. Now, why am I doing this? Well, because now I can say this is the limit as x approaches 0 from the right of, well, this is 1 over x to the negative 1 times the natural log of x, which if I want to move this negative 1 now into the denominator, I can. Then this is the natural log of x, keeping the limit out front from 0 from the right, of 1 over x in the denominator. Because again, if you were to bring it back, this could be negative 1, bring it back, this is positive 1, you're starting with what we have. So we haven't actually changed anything, we've just manipulated the way it looks. So we've actually written it as a L'Hopital's rule question now. Because we've written it as a fraction, we can now go ahead and employ L'Hopital's rule. From the right doesn't even matter in this question. So we can just go ahead and take the derivative. So this is equal to the limit as x approaches 0 from the right of the derivative of ln x we know is 1 over x, and the derivative of 1 over x, as we've shown earlier, is negative 1 over x squared. Now you may be looking at this and saying, well, if I plug in 0, I divide by 0. But we can adjust this again by using our rules of algebra. So this is the limit as x approaches 0 from the right. We could do keep, change, flip, right? So I'll do minus, pull the minus out front, 1 over x times, so keep, change, flip this, x squared over 1. Well, now one of these x's cancels out with one of these x's, and what we have is the limit as x approaches 0 from the right of negative x when you cancel this out, which is so much easier than trying to divide by 0. So you actually, if you alter this, it becomes something that's manageable, because now it doesn't matter that you're coming from the right. If you plug in 0, negative 0 is just 0. And so this is the solution to this question. So even though you may originally look at this and be like, oh, it's 0, because this is in indeterminate form, we can't say that 0 times infinity is necessarily 0, but we can show that this specific question will have a limit of 0. All right, last question. This one is going to be funky looking. So this one has an exponent with a variable in it, and the base is a variable too. So this should look familiar again if you've taken pre-calc. You should recognize that anytime we have an exponent that is a variable, what we're going to have to do is use a log. So either a regular log or a natural log. So here's what I'm going to do. I want to rewrite this thing right here. So I'm going to call it something else. Let's say y equals x to the 1 over x. I don't like this exponent here, so I'm going to use a natural log to get rid of it. This is what I mean. Instead of having this, if I natural log both sides, then I have the natural log of y is equal to the natural log of x to the 1 over x. But if you remember the log rule that deals with exponents, it says if you have an exponent inside your log, you can bring it to the front of your log and multiply it. And so this implies that the natural log of y is actually equal to 1 over x times the natural log of x, which is a lot easier to work with. I also will rewrite this as the natural log of y equals, if you have 1 over something, you can bring the thing that you're multiplying into the numerator and say this is the natural log of x over x, because we know that we're going to need some sort of fraction dealing with L'Hopital's rule. Because again, you have infinity. If you plug in infinity into 1 over infinity, you get 0. Infinity to the 0 is indeterminate form. So you can't solve this just by looking at it. So we go ahead and try to adjust the function, and this is what we get. So once we do this, we are still looking at the limit. So now we have to consider, though, that we've done something else to it. So now we're saying that the limit as x approaches infinity of, well, I called it y. So the natural log of y is equal to the limit as x approaches infinity. Well, when we solve the natural log of y, this is what we got. So it's actually the natural log of x over x. Well, this we can solve, right? We know that we can use L'Hopital's rule on this. So this is the limit as x approaches infinity of, well, the derivative of the natural log of x is 1 over x, and the derivative of x is 1. Now I can try plugging in. If I plug in infinity into 1 over x, I get 1 over infinity, which is 0. So what we get is that the limit as x approaches infinity of the natural log of y is equal to 0. So let me rewrite this. The limit as x approaches infinity of the natural log of y equals 0. But what you notice is we're looking, we call this y, right? X to the 1 over x. We want the limit of y, but we have the limit of the natural log of y. So there is a theorem of continuous functions that says that if you have, or of composition of functions that are continuous, that says if you have some sort of a composition, which is what the natural log of y is, and you have a limit or like that kind of a function, what you can do is you can actually take the natural log and you can pull it outside of the limit. So what I'm going to do is I'm going to rewrite this function because I want the natural log of y, which is x to the 1 over x. So this is the same thing as saying the natural log of the limit as x approaches infinity of y, which we know is x to the 1 over x. So I'll write y, but we know it's x to the 1 over x, which is what we're looking for. And this is still equal to 0 because that's just what it says here. This is what we're looking for. This is what this is right here. How do I get rid of a natural log? Well, again, this is your pre-calculus coming back. So getting rid of a natural log is using the exponent rule with an e. And so what I mean is the inverse of a natural log is e. So to get rid of a natural log, you're going to create a base of e and make these two things exponents. So the way that I write it is I make a big E here, a big E here. E to the natural log cancels out, and you're just left with this. So this tells you that the limit as x approaches infinity of y, and I will also say this is the same thing as we know as the limit as x approaches infinity of x to the 1 over x, because that's how we defined y. And that's what we're solving for. It's equal to e to the 0. Well, we know anything to the 0, any number to the 0 is just 1. So the limit as x approaches infinity of x to the 1 over x is equal to 1. And that is our final answer. All right. I know that this question probably is going to make you go, what the heck just happened? So again, a recap. We needed to use a natural log because we had a variable in our exponent and a variable as our base. We used a natural log to create a fraction. We then were able to use L'Hopital's rule and find a number, but then we remembered that we had a natural log still. Because this is a continuous composite function, we can pull the natural log outside of the limit. And we were able to write it like this, the natural log of the limit, since this is what we were looking for. We can then get rid of a natural log with an e, this undoes it, and then this gives us our answer. All right. As always, if you have any questions, let me know. That's the end for today. I hope this shorter video helps a little bit. And I will see you for the next video.